Hello and welcome once again. Today I am here with another module of advanced programming in R. Remember that I have told you earlier that why we are going to study these advanced programmings using R, because R offers us some really fascinating features of these kinds of advanced programming. Here in this module I am going to discuss about lexical scoping in R. Here what it actually does is it basically sets sets of rules which provide us how the values of some free variables will be taken from any environment. We will let you know what global environment is, what the some kinds of local environment is, and something like that. So let's start with the module and let's see what is there in the module. So lexical scoping in R means that the values of free variables are searched for in the environment in which the function was defined. You already know what an environment actually is, but let's have some recapitulation. An environment is a collection of symbol value pair. Every environment has a parent environment. It is possible for an environment to have multiple children. The only environment without the parent is the empty environment. A function plus an environment is a closure, or it will be called as a function closure. If the value of a symbol is not found in the environment in which a function was defined, then the search is continued in the parent environment. As we have already known in R, the free variable bindings are these kinds of bindings are resolved by first looking in the environment in which the function was created. This is called lexical scoping. So in particular, lexical scoping is a set of rules that determines how R represents the value of a symbol. R has two types of scoping: lexical scoping and dynamic scoping. Lexical scoping is an inbuilt rule in R which automatically works at the language level. Lexical scoping is mostly used to simplify statistical computations. That is why this is useful, this will be useful for us. Now consider the following example. Here we are defining f such that this is a function of x and y, and we have x plus y plus z within the body of the function f. Now in this example we have two formal arguments x and y, but there is another argument z. Here z is known as the free variable, so it will be called as a free variable. Therefore, the scoping rules of a language determine how values are assigned to free variables. Free variables are not formal arguments and are not local variables which are assigned inside of the function body. Now there are four basic principles in lexical scoping. So let's see what are they. Primarily, they are name masking, then functions versus variables. The next one is a fresh start, and the other one is dynamic lookup. First part is name masking, as you can see from here. So what does it mean? Consider the previous example that we have just discussed. Now if a variable is not defined inside a function, R will look one level up. Let's see how it does. So here we are assigning 4 within the variable within z, and here our function is f which, as we have defined it previously, this is the function of x and y only, and within the body we are defining x plus y plus z. Now if we give 2 and 3 as arguments, so we are writing f of 2 comma 3, then finally we are having 9. So basically it takes the value z is equal to 4 and then add up these 3 numbers, and finally we are having 9 as our output. So now consider the next example. This is a pretty simple one. Here f is a function, and we have defined x to be 1, we have and assigned y 2 to y, and then we are defining a vector c of x y, and then the function is concluded. Now, if we want to know the function f, then that will give us these sets of numbers, vectors of numbers 1 and 2. Now, consider another example. Here we are assigning 2 to x, and we are defining a function g which tells us that y is taking the value 1, and we are having a vector of x and y. So, let us see what the function g gives us, and here it gives us 2 and 1 as we have assigned x and y to be 2 and y respectively. The same rules apply here. The same rules apply if a function is defined inside another function. So, let us have a look. Consider this example. Here x is taken to be 1, and here h is the function which within the body of the function we are defining at first, we are assigning 2 within y, and then we are starting another function within this function h, which is I, and this says that z takes the value 3 with this assigning operator, and hence we are having the vectors of numbers c of x, y and z. Then we are closing these curled braces, and finally we are wanting to know the value of the I function, since this had been defined within the function h, and finally we are ending all the braces. So, in this example, look what is inside the function, then look where that function was defined, and so on, and look at all the way up to the global environment where x is defined as 1. So, it takes all the values, it looks up to all the values, and hence it gives us the desired result. Now, look at the other loaded packages. Now, run this program at your own, and then predict the output by running the R code. So, the output will be 1, 2 and 3, since here the values of x, y and z are defined to be x is equal to 1, y is equal to 2 and z is equal to 3, which have been defined in various steps. Some of them are defined within a function, some of them are defined within two functions as well, and one of them has been defined totally outside of all the functions. So, here the output is, as you can see, 1, 2 and 3. The same rules will apply when closures functions are created by another functions. So, the question is, what is closure? We need to know what is closure here. Closures introduces the closure of function written by another function. A closure can access its own arguments and variables defined in its parent. So, when closures functions are created by another functions, we will just look at how they interact with scoping. In the following example, the function j returns a function. So, what do you think this function will return when we will call it? Just look at the function. Here j is a function of x, and within the body of the function j we are assigning 2 to y. Then we are defining again a function within j, and here it is x plus 2 into y, and then we are having, so we are ending the function, the j function as well as the other function here. So, if we assign j1 to k, and then we want to know what k actually returns, then it will return 5. It seems a little bit magical, isn't it? So, how does R know what the value of y is after the function has been called? It works because k preserves the environment in which it was defined. The environment includes the value of y, as we can see here from this example. So it's a bit clear now how R checks all the values from the environment where it is created, from the global environment, and all these kinds of things. So things are getting clear by now. Now let's move on to the second part, which is functions versus variables. The same rules apply regardless of the type of associated value. Consider the following example that had been given here in the slide. Here I is a function of x, which is defined as 2x. So it will return the value twice we are giving. And the second one is, at first we are defining a function m, and then within m we are defining I, which is a function of x, and it is x plus 1. And then we are wanting to know I 14. That is the argument that we are giving is 14. And finally we are wanting to have m. So what do you think it will return? Just guess and then match the thing which we are getting with the original one. And here we are getting 15. So finding functions works exactly the same way which we had used in order to find the variables. So things are that simple here. Now suppose a function is defined as f. If the name of this function is used as a variable under another function, then R will ignore objects that are not functions while it is searching. Consider the example that had been given here. Here f is a function of x and it's giving the value x by 2. Now if we define n to be a function which takes f is equal to 20, and then if we want to have f of f, then we are closing the bracket, and then we are basically defining the function to be f of f, and finally we are wanting to have the value of n. So it will give us 10. So here when we are defining f is equal to 20 and f of f, then thereafter R returns the value of the variable without showing any error. So basically here also we are encapsulating a function within another function, and you can see what it actually returns. Now let's move on to the third part, which is a fresh start. When a function is called, a new environment is created every time. This is a thing which we had learned previously as well. A function cannot tell what happened the last time it was run. Each invocation is completely independent. What will happen for the first time you run the function, and what will happen during the second time? Consider the following example, then you can have some ideas regarding what exactly is happening here. Here we have specified a function j, and then we are defining it to be if w does not exist, then assign 1 to w, else you are going to get w plus 1. So else you are replacing w with w plus 1, and then we are indicating to print w. So this is what our function is, and here we are wanting to have the function j. So this is what the function is saying us. Now what does exist do here? It returns true if there is a variable of the name, otherwise it returns false. You may understand these kinds of things by now. But if it returns the same value 1 every time, then remember what I have told you earlier. This is because every time a function is called, a new environment is created to host execution. A function has no way to tell what happened the last time it was run. Each invocation is completely independent, mind it, it's totally independent. So don't expect anything from it. Now we have reached at the fourth part of this section, which is dynamic lookup. Lexical scoping determines where to look for values, not when to look for them. So basically it answers the question where to look at, not when to look at. R looks for values when the function is run, not when it's created. As you can know, the output of a function can be different depending on objects outside its environment. So let's consider the following example. Here f is a function, f is defined to be a function which is a square function basically. So here we are writing f to be a function which gives us x square. So just assign x 5 to x, and then if you call the function you will get 25, as simple as that. You all know that. Now again, if you substitute the value of f, value of x by 10, then you are going to have, if you call the function f, then you are going to have 100 here. So there is a function in R which is find globals, and it helps us to find all global variables being used in a function. It lists all the external dependencies of a function. So the question is, what does find globals do, since it's a totally new function, and it might be the case that you haven't come across this kind of function before. So let's have some idea regarding what actually the find globals functions do. Actually, it finds global functions and variables used by a closure. By now you know what a closure of a function is, or what a closure actually is. So basically it finds global functions and variables which are used by a closure. So let's consider the example which had been given here. Here x global is taken to be R norm 20. So basically we are taking 20 random samples from normal distribution, and we are assigning it in x global. And again the y global is taking the same thing, and here it's R norm of 20. So we are again taking 20 random samples from standard normal distributions. Both of these are taken from standard normal distributions, since the mean and the standard deviation haven't been specified, and still we haven't specified the seed values here. As we know, we should specify the seed value if we want to have the same kinds of values. So since we haven't specified the seed value, so we are going to have different sets of random numbers here. So here, so we have this x global and y global now. Now we are defining the function f, which is where within the body of the function we are defining x to be, we are assigning the x global values to x and the y global values to y. Now we are trying to plot y on x, and we are wanting to see what actually things are like. Again, if you want to have find globals then as an argument f, then you are going to have these many outputs which are given here. So basically this will give you the components which are this curly braces, this follows thing, this assignment thing, this plot kinds of things, and x and y. So these many components will be given by the function find globals when we are giving f as an argument. So this function lists all the external dependencies of the function as we have just discussed, and these are the thing which we are having here. So we can also manually change the environment of the function to the empty environment. Empty environment function is empty environment is an environment which contains absolutely nothing. If we type environment f, then empty environment, and then the function which we want to have, so what does it return? It shows error in f and could not find the function plus. So it will give us an error. This doesn't work because R relies on lexical scoping to find everything, even the plus operator as well. So it is never possible to make a function completely self-contained. So you can apply the same idea to do the other things. Since all of the standard operators in R are functions, you can override them with your own alternatives. So consider the following, the example which had been given here. Here also we are having a function, this is function of E1, and we are having these sets of arguments here, and finally look at the output that we are having. Here, since we have given E1 is equal to replicate then 20 comma 1 plus 2, so we are having this as our output. So here 1 has been added to any numeric calculation inside the parenthesis, as we can see from the R code as well. So in this example, this brace works because every operation in R is a function call, even if it does not look alike. This includes infix operators like plus. Control flow operators like for, if and while also are included within this, and subsetting operators like dollar and even the curly braces and many more are included within these kinds of function calls. So this is what basically the primary ideas of lexical scoping is. So in this module we have learned some kinds of basic ideas of lexical scoping in R. We had learned about how R takes the values of free variables from any environment. We have learned about some kinds of basic ideas of different kinds of environment that R offers us and something like that. In the next module, we are continuing the discussion of this lexical scoping, and there we will show some different kinds of examples, several examples with the missing functions, with functions, and many things like that. So let's stop here and let's see what is there in our next module.